Hello friends, I am Shailendra Kumar and I shall be solving some problems on the topic of this rotating rotation about a fixed axis. So the first problem which I have taken is about angular momentum of a conical pendulum. So let me explain what is conical pendulum. So there is a pivot, there is a mass, and this mass is doing circular motion about this axis. Say this is z axis. Now the question, say this is L and the angle made here is theta. Now the question which I am asking is, what is the angular momentum? Now asking angular momentum is not enough, because we have to ask about which point or about what axis. So for this problem I am taking say this point, so which is the center of the circle which is made by this bob, and then I will also calculate angular momentum about this point, pivot point. So let us call this O and let's call this pivot point P. So before I go to this problem, I would like to talk about angular momentum of an object which is moving in x direction. Say this is x direction, this is the object which is moving in this direction, here is the origin, and I am asking the question, what is its angular momentum? Again the same problem, about what point. So say about origin and say about some other point, say this point is B. It does not seem this object is rotating about any of these points, but in principle we can calculate this angular momentum. So this velocity is v and it is in the x direction, and say this distance is x, again in the x direction. So this displacement is x hat. So the angular momentum is defined as r, where r is the position of the object, and p, where p is the momentum when the object is at position r. So here the r is this x hat and p is this mass times velocity, that is the momentum in the x direction. Now the vectors are in the same direction, they are parallel vectors, so the angular momentum is 0. Mind, this angular momentum is about origin. Let us calculate angular momentum about point B. Then angular momentum about point B will be again r cross p. This is our formula. Now here with respect to point B, r is this. So take it r, and p is mb. This is r p. Now for convenience, let us decompose this r in two directions. One is parallel to the motion of the object and other is perpendicular to it. So let us call it y prime. So this will be minus because it is in the negative direction. Here it is x hat. So you can write it like x hat minus y hat cross m b x, and it turns out that this cross product is 0, as we have seen earlier. So the angular momentum about point V is minus m v y, and then y cross x will be minus z. So it is m v y in the positive z direction. So from here we see that for angular momentum we have to define about which point, or in principle which point or which axis we want to calculate the angular momentum. And angular momentum, okay, so for this conical pendulum Let us calculate the angular momentum about this point. So, say the object, so this is the tangent, so velocity of this object is this, and say mass of this bob is m, and this vector is r, then angular momentum about this point O for this conical thing will be r cross mv. But we can see that since it is tangential to this circular orbit, this angle is 90 degree. So, this becomes m v r and in the z direction, and that is a constant. So, the angular momentum about this O point is a constant. Let us calculate the angular momentum about this point, pivot point P. So, this is about point P. So, here this is vector, call it vector L, say this is vector L, this is vector V. So, with respect to point P, the position of bob is vector L and its momentum is in this direction, which is mv. So, the momentum, angular momentum is L cross mv. Now, this you can write like mvl, and the direction will be perpendicular to this plane. Let me make it separately here. So, this is your L and this is your V. So, the direction will be perpendicular to this plane. So, say this. So, let me call this direction to be P. Now, as this bob moves on this circular orbit, the angular momentum with respect to this pivot point moves, it is like that, it is perpendicular to the plane. So, this is V and this is L, this is your LP. Now, as you move, as this bob moves, say it goes here, the angular momentum takes this direction. So, earlier we saw that with respect to this point the angular momentum is constant, but with respect to this point P it is changing, though its magnitude is constant, but its direction is changing. So, if we put this thing here, this here, then we see that it actually sweeps a cone, and if you decompose it, then we see that in the z direction the momentum is constant, in the up direction the momentum is constant, but in the horizontal direction it is changing its direction. So, it is varying continuously. So, with this we have calculated angular momentum of this conical pendulum with respect to 2 points. With respect to this origin it is 0, and with respect to a pivotal point it is constantly varying. So, the next problem I have, it is about moment of inertia. So, for simplicity I would take disk. So, this is problem number 2. So, take a, let us calculate moment of inertia of a disk. So, let us calculate its moment of inertia. Now, the point is, to calculate moment of inertia we have to again define about what x is. So, let us take an axis which is passing through the center of mass of this disk and it is perpendicular to its plane. So, about this axis. So, we know that moment of inertia is defined as suppose mass is a small mass and its distance from the axis, perpendicular distance from the axis is r, then dm times r square, then integrated over the whole object. So that is the definition of our moment of inertia. So let's make the schematic disk here. So let's take a small portion of this disk which is at a distance of r, and then this distance is dr. This distance is r times d theta, where d theta is this angle. Then mass of this small chunk, say dm, will be mass density of this disk. Say mass density of this is sigma, then sigma times area of this chunk. The area of this chunk is r d theta dr, and sigma is, if the total mass of this disk is capital M and say radius is capital R, then sigma is mass divided by total area of the disk, which is pi r square. So this is your sigma, which is a constant here because the disk is uniform disk. So inertia, moment of inertia will be sigma r d theta dr r square, and the integration goes for theta, it goes from 0 to 2 pi, because we have to take the whole complete this loop, and for r it goes from 0 to capital R. Now we integrate it, we get sigma. For theta integration we get 2 pi because there is no theta dependence, and for r integration we see this is r square, here it is r, so r cube, so its integration will be r raised to the power 4 by 4 from 0 to capital R. So it is 2 sigma pi r4 by 4. If we put the value of sigma, we see that I turns out to be 1 by 2 m r square. So this is the moment of inertia of this disk about center of mass axis. So let's put center of mass axis. Now let's ask, what is the moment of inertia about a tangent about say this axis, which is parallel to the axis which is going through the center of mass and perpendicular to the plane of the disk, but it is actually touching the disk. So what is the moment of inertia about this axis? So for this axis we will use parallel axis theorem, which says that if you know the moment of inertia about center of mass and you want to calculate moment of inertia about some axis which is at a distance of d from the center of mass. So here the distance is r, then this should be added to the moment of inertia with respect to the center of mass axis, that will be our total inertia. So here inertia will be about this axis will be ICM is half mr square, then plus mr square. So it will be 3 by 2 mr square. Then we can ask that we know moment of inertia of this disk about this axis. What is the moment of inertia about some axis which is along the diameter? So that means we are actually rotating this disk in this direction. Then we are asking what is the moment of inertia about this axis. which is along the diameter. So, for that we use perpendicular axis theorem. This theorem says that if you have 3 axes x, say y and z, then moment of inertia of say z axis will be moment of inertia of x axis about x axis plus moment of inertia about y axis. Now, here we know this moment of inertia ICM, call this z, call this x. Then from symmetry we see that if this is the y axis, then moment of inertia about this axis, say it is Ix, and moment of inertia about y axis, say it is Iy, they should be same because of the symmetry. The object is symmetric, whether you are rotating about x axis or whether you are rotating about y axis, it should be the same. So, say it is I, then Iz, which is actually the moment of inertia about center of mass, is Ix plus Iy, which is 2I. So, I about a diameter, call it diameter, will be I about center of mass divided by 2. Now, we know that ICM is half mr square. So, I diameter is 1 by 4 mr square. Similarly, one can ask that what is the moment of inertia about an axis which is tangential to this disc and parallel to the diameter. So, you can use parallel axis theorem and do the same analysis which we did here, and you can calculate moment of inertia about this axis. The next problem we have taken is rolling without slipping, and so this involves two motions. There is rotation also and there is translation also. So, I have taken a problem which is a cylinder which is rolling down an inclined plane. The inclined plane has rough surface, so that it can stop the cylinder from slipping. It provides that much friction that it does not slip. So, this is the say this is the cross section of the cylinder, and this is the surface of the inclined plane. This is making an angle of theta with the horizontal. It is rolling downwards, so it has an acceleration, linear acceleration, and our objective is to calculate this. If it were a simple sliding motion, then we could have calculated it very easily, but here rotation also involved, so we have to take care of that also while we are calculating this acceleration here. So, this is the z axis coming out of this paper. Let us take this to be the x axis and let us take this to be y axis. Let us take mass of this cylinder to be capital M and the radius to be capital R. So, the equation, we shall write equations of motion. For that we shall write torque equation. So, to calculate the torque, we shall calculate the torque about this point, call it origin, and say this is R vector here. So, before we calculate the torque, we should know what are the forces acting on this body. So, let us list them. So, first force is weight of this cylinder. If it is W, then it should be mass times gravity in magnitude, and other force is the normal reaction. So, call it capital N. Since there is friction also, so that is in this direction, friction. So, these are the forces acting on this object. Now, for to write the equation for torque about this origin, we have to calculate R cross F, where F are all the forces, R is the distance, where F is the force acting on this body at the center of mass of this body. And other force for friction, see the perpendicular distance of this friction from the origin is 0. So, let us not write it in the equation. So, that is actually 0. So, this weight can be decomposed into components. So, this is theta. So, this should also be theta, right here it is theta, and then this component of the weight will be W sin theta, and this component of the weight will be W cos theta. So, this W sin theta is actually trying to rotate it in this direction. So, this is a clockwise direction. Let us take clockwise direction to be negative, then minus force W sin theta, and perpendicular distance of it from the origin will be this. So, that is actually the radius of this cylinder. So, that is R. Then this W cos theta force is trying to rotate it counterclockwise, and this normal reaction is trying to rotate it in the opposite direction, clockwise direction. So, or simply we can say that an actually cancels W cos theta. So, the torque about this origin because of the total effect of an and W cos theta will be 0. So, let us not take into account. So, this is the only torque about origin acting on this cylinder. Now, let us write equation for angular momentum about the same point. So, the angular momentum here we have to consider this thing that this object is rolling. So, because of that rolling, the angular momentum about point about origin is moment of inertia about the center of mass times omega, that is the pure rolling angular momentum because of pure rolling. And since it is rolling in this direction, which is clockwise, we have to take a negative sign here. That is our convention, nothing else. And then angular momentum of this cylinder with respect to this origin. So, that will be this R cross, say this is moving in this direction and it has a velocity at any instant. So, its momentum will be m times v. So, that is the additive angular momentum because of the translational motion of this cylinder. Now, this we can calculate R cross mv. So, we can calculate this momentum. So, this will give you component along this will be R times mass times v, and other component will be 0. So, and we know that this instantaneously this point is static. So, with respect to this point, the velocity v is actually r times omega. So, this momentum is m r square omega. So, the angular momentum turns out to be its magnitude turns out to be m r omega here, and this is actually a disc. The cylinder, you can treat a cylinder as a disc. So, we have already calculated moment of inertia I omega in the last problem, which is 1 by 2 m r square omega, and here is a minus sign, and this angular momentum is actually clockwise. It is clockwise, so it should be a minus sign here. So let us put a minus sign here. It will be minus 3 by 2 mr square omega. But we know that rate of change of angular momentum is the torque acting on the object about the same point or origin. So let us derive this. So it will be minus 3 by 2, m is constant, r square is constant, maybe omega is changing. So d dt of omega, because of acceleration omega of course will change. So we can only derive this thing, and tau naught we have already calculated it, r w. So w is mass times g sin theta. So if we calculate it, then d dt of omega minus minus cancels, and this so d dt of omega minus minus cancels. So here it is 2, mass cancels, 1 r cancels. So this is 2g sin theta by r by 3. As we can write v is equal to r omega, so if we derive it with respect to time, so r times d dt of omega. So this is the linear acceleration which we want to calculate, r times d dt of omega, which we have already calculated. So here a turns out to be r times d dt, which is this, put it here. So a is equal to 2 by 3 g sin theta. So that is the answer. So here we had to do this all this exercise because both rolling and rotation and translation both are involved in this motion. Okay, with that we move on to our next problem. So this problem is based on energy, so rotational energy and kinetic energy. So based on that, this problem is like we have a rod which is actually put on a surface, and this surface is smooth. The mass of this center of mass, say, of this thing is here, and it is held here, and then we release it. It starts falling. When it starts falling, since there is no horizontal force acting on this rod, the center of mass will actually fall vertically downwards. So say after some time the center of mass is here, and the position of this rod will be like this, something like this. I have made it a bit thicker, so let's So our objective in this problem is to find the velocity of the center of mass. So for that, we know that total energy, which is kinetic energy plus potential energy at initially when this rod is not falling down, is this, where k naught is 0 because the object was not moving, and u naught is mass times gravity times the height of the center of mass. So say the length of this rod is L, then this will be L by 2, so it is L by 2. So, this is the potential energy in the beginning. When this center of mass moves a bit downwards after some time, say this direction is z direction and it has moved this distance z downwards, and say as this rod falls down, its inclination with respect to the vertical actually increases. So, initially with vertical it is making angle 0, now the angle, this angle, let me use another color here, this angle theta is increasing. So, we want to find its velocity with respect to theta, assuming that we can measure theta. Theta is the angle. So, after some time, at a later time, this kinetic energy is because of two motions, rotation of this rod with respect to its center of mass and its translation from this height L by 2 to some height L by 2 minus z. So, the rotational kinetic energy will be half I about Cm times theta dot square plus half m, this is kinetic energy, this z distance is covered, so z dot square. And potential energy at a later time will be mass times gravity. So, this is the energy in the beginning when the mass is here. When it falls down this distance, so this is the energy which is converted into the kinetic energy. So, that let us subtract it. So, it will be mass times g times g. So, you can write this as mg L by 2 minus z, that is the potential energy. Now, since this surface is smooth, there is no dissipation of energy, we can use conservation of energy here. So, conservation of energy suggests us that we can write k plus u is equal to k naught plus u naught. So, that is half I Cm theta dot square plus I m z dot square, z dot is the velocity in the vertical direction, plus u. So, u will be mg L by 2 minus z is equal to, here kinetic energy k naught is 0, 0 plus mgl by 2. Now, we shall solve this equation and we shall find this thing, this z dot, this is what we are after in terms of theta. So, we shall now get rid of this z because we do not know that, and this theta dot. So, let us do that. First of all, we can see here that this thing actually cancels this. So, we have ICM theta dot square plus m z dot square is equal to 2 mg z, correct. Now, for a rod, moment of inertia about center of mass and perpendicular to its length is actually mass of the rod times its length square divided by 12. And for theta, so this was the initial position of the rod after some, so this is the center of mass. After some time the center of mass reaches here, the rod is here. So, this is the angle theta. So, this is z, this whole distance is L by 2. So, we see in this triangle, or rather let us go to this triangle. So this theta is cos theta will give you this thing divided by this thing. So this thing is L by 2 and L by 2 minus Z actually, and this thing is L by 2. So we see that Z is actually L by 2 1 minus cos theta. So from here let's take its derivative, then Z dot is equal to L by 2 derivative of cos theta will be sin theta, actually minus sin theta, so I will remove minus here, and theta is a function of time, because as time passes this theta varies, so we have to take its derivative. Okay, or in our language we shall write it L by 2 sin theta dot Z dot. So theta dot is equal to 2 by L sin theta C dot. So we shall substitute these things in the last equation, in this equation here. So ICM is m L square by 12, theta dot is 2 L sin theta Z dot square plus m Z dot square is equal to 2 m G Z. So we solve it for Z dot and we get Z dot square is equal to 2 GZ divided by 1 plus, so this is 4, this is 3, L square cancels with L square, so sin theta, so 1 by 3 sin square theta, or if I remove this 2 from here, then square root here. Now again we want this is actually our velocity which we want to find, this is our objective, but this is in terms of Z, we want it in terms of theta. So from here we see Z is equal to L by 2 1 minus cos theta, so Z dot is now square root 2 cancels with this 2, then GL 1 minus cos theta, we can solve the denominator also, so it will be 1 plus 3 sin square theta, 3 sin square theta. So this is the answer. So in this problem there were two motions, that the rod is rotating, at the same time the center of mass is falling, and the only motion is there, motion of the center of mass is the vertical motion, there is no horizontal motion because the surface is smooth and there is no force in the horizontal direction. So in these 4 problems I have tried to cover angular momentum, moment of inertia, the parallel axis theorem in that context, and perpendicular axis theorem. And then the third problem was based on this rotation with translation, where we had assumed that there is no slipping, so ruling without slipping. And the last problem was based on energy. So this problem was solved with the energy concepts, that there is rotational energy, there is kinetic energy, and energy is conserved when there is no mechanical dissipation. So with that I wrap this up. Thank you.